Hello. In this example video, we're going to be looking at a matrix, and we're going to ask the following question about a matrix, namely whether the matrix is orthogonal or not. The matrix we're going to look at will be given as follows. So it will be a 4x4 matrix whose entries are in the first column 0, 0, 1, and 0. In the second column, 8/17, 0, 0, and 15/17. In the third column, 0, 1, 0, 0. And in the last column, minus 15/17, 0, 0, and 8/17. The question asks whether this matrix is orthogonal or not. And obviously, to answer this question, we need to know what an orthogonal matrix is. A matrix is orthogonal when the columns of the matrix form what is called an orthonormal sequence. In the some people also call it a set because they don't know the difference between the sequence as a set. So another name for it would be orthonormal set. So for a sequence of column vectors to be orthonormal, it means for each vector to have norm 1. In other words, the dot product, the inner product of that vector with itself must be 1. And also for any two vectors in the sequence that are different terms of the sequence, that they're not the same term, like for example the first one and the second one, any such two should be orthogonal to each other, which amounts to their inner product being 0. So to check whether the matrix is orthogonal or not, what we need to do is to check that its column vectors satisfies all the conditions that we stated here. Now, these conditions that I stated about the column vectors is actually not the original definition of an orthogonal matrix, but rather a theorem that gives a characterization of orthogonal matrices. The original definition states that the matrix is orthogonal. Well, it also depends on how one defines something and what one calls definition and what one calls a theorem. But what I'm assuming is that the definition is given by the statement that the transpose of A is equal to its inverse. So A inverse is equal to A transpose, which is equivalent to say that the transpose of A multiplied by A is the identity matrix. So to check that A is orthogonal matrix, we can either check that its transpose multiplied by A is identity matrix, or to check the thing we stated about the column vectors. And it turns out these two things are equivalent to each other, which is established by a theorem. And it is also a bit kind of like almost like obvious to say that they're equivalent to each other because of what I'm going to say right now. So if I set up the transpose of A, it's of course the transpose is taking the matrix and flipping it around along the main diagonal. So that's why I marked these things with yellow. So the diagonal entries will stay the same, and all the entries will hop on the other side, right? So the 8/17 there will give me 8/17 here. On the other hand, 0 here gives me 0 there. And the same for that 0 there. That comes down. Oh, sorry. That 0 becomes 0 here, and the one that was here becomes 1 there. Then the last entry here, we had a 0 in this corner, so in that corner in the transpose we'll have a 0, and here we'll have minus 15/17. And what about the other entries? So what about those two, this one and that one there? So they swap around, it'll be 1 and 0. And these two swap around, these two. So we'll have 0 and 15 over 17. And finally we are left with these two. And they will be still the same 0, because in both cases we had 0, so nothing swaps around. So this is the transpose of A. And now what we want to do is to multiply the transpose of A with A. Maybe I'll just copy paste the A instead of writing it out again. And when we do the multiplication, in order to establish orthogonality, what we want to get is that this product is equal to the identity matrix. So this is supposed to be equal to the identity matrix. Which is given by ones in the diagonal and zeros everywhere else. So that's what an identity matrix is. Okay. Now, how do we get this equality? Well, we compute the left-hand side and then we see if we get the right-hand side, right? Now, in computing the left-hand side, it will turn out that, and it's not difficult to see that by the way matrices multiply, that each entry of the left-hand side is... So how are the entries of the left-hand side determined here? What's going to be the entry here? It's going to be, I'm going to mark this with green. It's going to be this thing, term by term multiplied and then summed up with that thing. But that's basically taking the first column and taking its inner product with the first column, with its taking its inner product with itself. In other words, taking the matrix multiplication of this with its transpose, right? So what we end up getting here is the inner product of this thing with itself, and of the first column vector with itself. And also, so the same applies for all the other diagonal entries. So when we compute the product of the two matrices here, what we will have in the diagonal entries will be the inner products of each of those column vectors with itself. And remember, with orthogonality of a sequence of vectors, we want the norm to be 1 for each vector, so we want the inner product of a vector with itself to be 1. And so saying that these diagonal entries match with the diagonal entries here, sorry, you didn't see the diagonal entries down here. So to check that these diagonal entries here match with the diagonal entries here is just checking that the each of the column vectors has length 1, in other words, norm 1. On the other hand, all the other entries in the product of the two matrices, all the other entries here will be, what will they be? They will be a row of the matrix multiplied with a column of the matrix, seen as row and column vectors, right? But the rows of this matrix are transposes of the columns of that matrix. And so what the other entries end up being here are the dot products of two column, the inner products of the two column vectors of the original matrix in those cases where these two column vectors are different columns. And so in each case of the entry, right, for each such entry we need to get a value of 0. And so we are basically then saying that any two vectors in that sequence of column vectors, any two vectors must be orthogonal to each other. And so this is how we establish that checking that a matrix is orthogonal can be done either by multiplying the transpose of the matrix with A and checking that it's the identity matrix, or equivalently by making sure that its sequence of column vectors is an orthonormal sequence. So in terms of computation, none of this is quicker than the other one, and so it doesn't matter which one we do. It's just a matter of presentation as far as their difference lies. Okay, so let's see if the product of these two matrices ends up being that matrix or not. So let's begin with the with figuring out this entry here. So taking the dot product, the inner product of, taking the matrix product of this row with that column is going to give us 1. So that seems to work out fine. And then this one with that one, because of all the zeros, so in each case, either this has a 0 or that the other one has a 0 for the corresponding entry. So because of that, the result here is 0. Okay, and so again, this multiplied by that, the result is 0. My matrix space is bigger than I needed, I think. And then finally, also here we see 0 multiplied with that, then 0 multiplied with 0, 1 by 0, 0. So it does end up being 0 there. Okay, great. Now let's look at the second row. So 8 over 17. So basically what we need to do in this for the second row, we need to multiply the second row here. For the first entry there, we need that with the first column here, right? And you can see that it's all zeros because never ever we have a non-zero term here, and the same term there is non-zero. So it ends up being 0 indeed. And now let's look at the second row with the second column. So this is 8 over 17 squared plus 15 over 17 squared, right? So what is that? Let's calculate that on the side. 8 over 17 squared plus 15 over 17 squared. Okay, so 8 squared is 64. What is 17 squared? 10 squared is 100. Well, maybe the better way is to multiply 17 by 10, which is 170, and then multiply 7 by, okay, let me rather write this down. Talking and thinking don't always go well together, so 17 times 17 equals 17 times 10 plus 7. Is this the best way of thinking about this? Maybe a better way would be 20 minus 3 times 20 minus 3. Okay, so 20 times 20 is 400. Then we have minus 60 here and minus another 60, which is 120. And then we have plus 9. Okay, 400 minus 120 is 280 plus 9, so it's 289. So 64 divided by 289, and then we have plus 15 squared is, I think, 225. 15 squared is 15 times 10 plus 5, which is 150, plus 5 times 15 is 50 plus 25 is 75. And so that does give us 225. So we have 225 here divided by 289. And 64 plus 200, and sorry, that line wasn't visible there. 64 plus 229 is exactly 289. Wow, that does work out to be equal to 1. And that's what we wanted if we wanted that equality of matrices to hold, right? So it does work out to be 1 here. And then for the next entry, sorry, there we go. For the next entry, we need to multiply this row vector with with that column vector, and we can see that that thing is going to be 0. And the same for the last one, right? This is that times that one. It's 8 times 15 with a minus sign, and then 8 times 15, 15 times 8 with a plus sign. And so they together will give us 0. So the next two entries there are zeros. And then we move to the next row, the third row here. That times the first column here, that's going to be 0. Okay, so as we continue this calculation, we come to realize that because as we said, in each entry here, each ijth entry is the transpose of the ith column of the original matrix multiplied by the inner product of the inner product of the ith column inner product of the ith column multiplied with jth column of the matrix. No, I didn't make sense now. Inner product of the ith column of the matrix multiplied by the jth column of the matrix. That's the ijth entry. But the inner product is commutative. You can swap the order around. So the effect of this is that the matrix we're getting out here is supposed to be a symmetric matrix. And so we don't have to check all the entries. We just have to check on one side, and the others will be reflected around. We do have to check the diagonals, but the zeros now will be reflected around. So because we've got all the zeros here, we will also get zeros here and there. So that reflected here gives that. And we still have to check whether this is 1 and that is 1 or not. But otherwise, then this will be a 0 as well. And this must be a 0 as well. Wait, sorry. What's happening here? So we still have to check this entry as well. So that leaves us to check this entry as well. But then the other entries are 0, 0. And of course, in terms of the column vectors, in terms of the orthonormality of the column vectors, this is just saying that if angle between one and the second vector is 90 degrees, if they're orthogonal, then the angle between the second and the first one will also be 90 degrees. Well, maybe minus 90, but it still counts as orthogonal, right? So we don't have to compute the whole matrix. We just need to compute one triangular half of it and then reflect it around the main diagonal to get the other. So that applies when we multiply a matrix with its transpose. It wouldn't always work for any matrix, right? Okay, so what remains to check is these 4 entries, and so for that we're going to for this first question mark here, this is an entry at I being equal to 3 and j being equal to 3, right? So we have to take the third row here and the third column here, and we take their product. It is indeed 1. So this is indeed 1. And then the third row with the fourth column, and we see that at each spot either one has 0 or the other has 0, so the answer ends up being 0. And then in the last row, we need the third row and the fourth row and the third column. So this will be the last row of this and the third column of that. And once again, we have zeros at either one place or the other place when the for the corresponding entries. So this is going to be 0 as well. And finally, for the last entry, we have minus 15 times minus 15, which is, we don't need to know what it is because we already know what it is, right? It's the same as 15 times 15, and 8 times 8 is 64 as before, so it's exactly the same calculation. that gave us the answer 1. So here also we have 1. It's not exactly the same calculation, technically speaking, because here we have minus 15. Previously we had plus, but when we square it, that minus goes away. So you see, it did turn out that A transpose times A is equal to identity matrix, which then confirms that the matrix we started off with, this strange matrix with some zeros being zeros and ones and the others being very strange fractions, turns out to be, after all, an orthogonal matrix. And that completes the aim of this example video.